Okay, now back to how do you build this MAC, or first of all, what is a MAC? Okay, so in the symmetry key setting, there is a key that Alice and Bob would already have, and they would like to authenticate any number of messages. Okay? Always when I say any, any feasible number of messages. Okay, so here is my Alice and Bob. They look like this now. There are different algorithms now, like MAC and verify or good. So again, now there are three algorithms: key generation, generating the MAC itself, and verifying the MAC. And I didn't mention explicitly correctness for encryption. It was there, it was needed that when you encrypt and then decrypt, you should get the same message. Here, correctness is if you use the right key, if you use the same key to produce a MAC, okay, so this MAC KM is a MAC tag, and you feed that into the verifier along with the same message M, the verifier would accept. So verify equal to 1 means verifier is accepting, otherwise I would say verify equal to 0. Right? And what is the security definition? What's the security requirement? It's what you would expect. Suppose you have an adversary who sees a lot of MACs on a lot of messages. Lot of messages of its choice. Okay? So that's what this back and forth here is. It can query with some message MI and get back at MAC tag SI as many times as it wants, and then it tries to produce a forgery. Again, it's an arbitrary message of its choice along with an attempted forgery or tag, and we will check if the verifier accepts or not. And in this experiment, unlike what we're talking about for encryption or pseudo-randomness, where it was about distinguishability, here it's a winning probability. The advantage is the probability that the verifier accepts the forgery, that you're able to produce a successful forgery and you did not cheat. As in, there's a trivial way you can produce a forgery, which is just request that message to be signed by the actual MAC algorithm. That's not a forgery. So for you to win, that message should not have been queried. Or what I've written here is a little stronger. It says, it's a little stronger security guarantee. What it says is that I will consider the adversary as cheating only if this M comma S is exactly an MI comma SI from before. So I'll still consider it a valid cheating if the adversary send a message, got a tag, and the forgery was the same message but with a different tag. I'm calling it a forgery here. Okay? There is a weaker form of the definition where I will not consider it a forgery if it was on a message that the adversary got a tag on. Okay? So I'll pause for a second, make sure you understood the definition. So any questions on the definition? Okay, so again, the plan is simple, or the security requirement is simple. The adversary gets to, so the key is generated, given to the MAC algorithm, the verifier, so that's all part of the experiment. Then the adversary comes along and starts querying the MAC algorithm with messages of its choice, gets back MAC tags, and when it's satisfied at some point, it tries to produce a forgery, and it succeeds if the forgery is accepted as a valid MAC tag by the verifier, and it was not one of the query response from the oracle. Okay? That's what and so the security definition is that for every feasible adversary, the probability of the adversary winning in this game, or its advantage here, should be negligible. Let me kind of demystify MAC a little bit. Here's a very trivial kind of construction. Doesn't need any cryptography really, just randomness to do one-time MAC. In spirit, a little bit like one-time pad, right? Which didn't need any cryptography beyond XORing. Here you don't even need XORing. But let me show you this one-time MAC. So to sign an n-bit message, what you do, it's not very efficient, so it's kind of, there's a lot of bloat. You pick 2n strings, okay? And each string is k bits long, where k is, think of it as 128 bits, right? So your security parameter. So there are 2n strings here. I've arranged them as pairs, right? I marked them as, they're in the form RI0 and RI1. The I indicates the bit position, and 0 and 1 presumably is going to be the bit value, right? A bit can take value 0 or 1. Okay, but for now, these are all part of the key. This is our shared key. Okay, so just flipped a bunch of random coins. And now suppose I want to tag authenticate a message 010. I want to use my key to produce a tag, right? Here is my tag. I just look this up at, so first position is 0, so I pick R10. Second position is 1, so I pick R21. And third position is 0, so I pick R30. Okay, so 3 k-bit strings. I just put all of them together and send that as my MAC. Verifying is exactly the same. Verifying here is actually to say you compute the MAC yourself and check if it's the same MAC as what is sent to you. So when you get a message, you compute the MAC yourself and compare it with the MAC you got. And I'm claiming that this is actually a secure MAC. Okay, secure, as in you only negligible probability that an adversary can cheat, will be able to forge. Why? So what can Eve do? So there's a deterministic algorithm, by the MAC. Once you fix the key, so we don't have to make this distinction between the weak security and strong security of the MAC I was talking about last time. So for every message, there is a single MAC tag. The adversary has queried for a bunch of messages, and then it created a forgery on another message. Now this, let me take that back. This is a one-time MAC. So the adversary has queried for one message, and now it has created a forgery for another message. So this one message and this other message are different. Otherwise, it's the adversary doesn't win. Right? They're different at least in one position. Okay, so they are different for now. Say the first position. Say the forgery. So this was what it queried. Say 010, and its attempted forgery starts with 1 something something. Well, for that, the only way the adversary can get the verifier to accept is if it can guess this R11 exactly. And that's a 128-bit random string. The probability of guessing it, and has not seen that. Right? So the probability of guessing that, given what it has seen, is 1 over 2 to the 128. Okay, so that's why it's a secure MAC. So any questions on this? Make sense? All right, so that's very simple. Why don't we use it? It's computationally, it works against computationally unbounded adversaries. No cryptography needed. There are two problems. One is it's one time, and secondly, it's really inefficient, right? What we usually would like to see is that you have these gigabytes long messages, and the MAC tags are some short things. Here, the MAC tag is much longer, 128 times longer than the message itself. Okay? So that's not going to fly. However, much more efficient one-time MACs exist. Okay? So, and they do get used inside other constructions of MACs also. And of course, here it's limited, right? It's only one time, so that's all you can do. Or one time or limited number of times is all you can do if you want security against computationally unbounded adversaries. Okay? But that's kind of a good starting point for some MACs. But I want to kind of give you another MAC based on what we already have seen, and that's a PRF, right? So I want to give you a MAC from a PRF. Let's start as before for encryption. Let's consider the case when the message is a single block. Okay? Well, the construction is this. Just use a PRF and it is a MAC. What do I mean by that? You actually feed the input, the message as the input to the PRF and take the output as the MAC. Why is it a MAC? Well, and I'm claiming you can do it for any number of times, any number of messages. They're all one block messages, single block messages. Well, because there's a random, PRF is indistinguishable from a random function. So to guess the MAC tag would require the adversary to guess the output of a random function on a point at which it has not queried the random function. And again, it's, so let me see if I have, so there's just a picture for this very complicated construction, I guess. There's one thing that I kind of glossed over, that the output length of this MAC tag should be long enough. The output of the PRF should be long enough. So for encryption, it was not really needed, right? It's just an efficiency question how big the output of the PRF is. Here, for a MAC, I really want this output to be long because I said, of course the PRF is indistinguishable from a random function. But if the random function's outputs are short, it's very easy to guess. You can just randomly guess and you'll get lucky. Right? If it's a 5-bit output, with probability 1/32, you can guess it right just by guessing it randomly. So we do need the output length to be long enough, the output to be long enough. But otherwise, there's a PRF. Security is, okay, let me take a minute to kind of give you a reduction. A reduction is a very typical way of doing a security proof. So here is how it goes. So we said, okay, if the claim is, here is a construction for a MAC based on some other cryptographic object, namely a PRF. And a typical security proof would say, suppose you have an adversary for my MAC. Suppose you claim that my MAC is not secure, then I will show you that this PRF is not secure. Okay, I will turn your adversary into an adversary for the PRF. And if I can do that, and then, if you also tell me that the PRF is actually secure, PRF doesn't have an attack, then my MAC doesn't have any attacks against it, right? So that's what a reduction is. I take an adversary, purported adversary for the MAC, show how to change it into an adversary for the PRF. And, so I'm leaving it as a thing for you to think through, right? How do you, suppose somebody forges. Okay, you want to kind of say, look, that forgery can be used to tell the difference between a PRF and a true random function. The idea is going to be that if it were a true random function, there is no way you could have forged, except with this 2 to the minus m probability. M is the output length of the PRF for the random function. Whereas if you have an advantage epsilon against the MAC, then I can distinguish between these two cases with probability which is proportional to this difference epsilon and 2 to the minus m. So I leave it for you to think through that. Actually I have it on the slide, but not. You can read it offline. Okay, so the bottom line is that for single block messages, there is a very straightforward construction using a PRF. But we'd like to do it for multiple block messages. Now for encryption, I said there's a trivial solution. It was just a matter of efficiency. You could have, the trivial solution was you could have encrypted each block independently, and then you'll be blowing up the ciphertext size by 2. But it's secure. It was secure. Why not do the same for MAC? Just as a starting point, right? Well, unfortunately, with a MAC, that's not true anymore. If you just separately MAC each block and send them all together, that's not going to be a secure MAC. Do you know why? Or can you think of why? So I have a 10-block message. I want to authenticate it. I authenticate each block separately and send all of them, send the authentication tag for all 10 of them, along with my 10-block message. What can go wrong? Yeah?
There are 10 keys, so we made it like...
There's only one key I'm using. It's not a one-time MAC. I have a MAC and a PRF, right? I can use that one key to authenticate any number of blocks. I used it to authenticate these 10 blocks. MAC is deterministic, that's not a problem. You know that I said my message is block 1, block 2, suppose they are the same, tag 1, tag 2 will be the same. So what, right? There's nothing I'm trying to hide here. Let's make it simple. Suppose 2 blocks, right? I have, let's say, A, B. A is a block, B is a block, let's say. And I have tag for A, tag for B. So as an adversary, what do you see? The message is AB, and I have tag 1, tag 2 going with it. Can you create a forged message? Can you create a MAC, a tag for BA? The message BA? Sure you can, right? Just it will be tag 2, tag 1. Or BB, you can do that. Or you can drop, you can just have A, right? You can create a MAC for A. So if you just independently, MAC'd or authenticated each block, the adversary can just take one such thing and rearrange it. Or it can take 2 such messages, splice them together. It can drop things, all of that, right? So that won't do. It's not that you want to authenticate individual, or to kind of make it an extreme thing. Suppose you're authenticating, your block is tiny enough, you're authenticating each character in English. Well, you listen for a bit, you ask for a few things, you ask a tag on, what is it, the quick brown fox, whatever, right? The thing, pangram, it has all letters in the alphabet. And you've got tags for all the letters, and now you can create, MACs for anything, right? So that's certainly not a good idea to individually create a tag for each block. So there are 2 solutions. First, there are many solutions. I'll just show you first something that's very straightforward, doesn't involve any complications, and then something which needs a proof, which we won't do. So here's a trivial solution. Okay, I want to, well, it's not that trivial. You need to think through it to make sure it's correct. You want to kind of tie the blocks together, right? You want to say, look, this A, B, C, they are in that order. A is 1, B is 2, C is 3. So why not, instead of tagging A, B, C separately, why not write that round, right? The first letter or first block A, second block B, third block C, and then I'll create an authentication tag for first block A. So I'll prevent you from rearranging things. Okay? Is that good enough? So, for each block, I have a serial number, the block number, and I've tagged those blocks. So now you cannot rearrange them. It has to come in the right place. What else? What can the adversary still do?
It can consider that it has a one-to-one mapping for each of the message blocks that it can assume that.
I think there's no confidentiality or anything. I'm not sure what your concern is. So, sure, MAC is deterministic. One A has a particular tag. It'll always be the same tag. If there is another message which is A, X, Y, that A tag will look the same. Yeah?
We can also send the tag of the next message along with the message.
Are you proposing an attack, or are you trying to?
Trying to solve the issue.
But what is the issue is my question. Why is there an issue?
Changing, so nobody can change the order as we have.
I already fixed that issue, right? I give you I put this 1, 2, 3, so nobody can change it. No, but I want to see what's wrong, what further problems are there with this solution. Are there any problems with this solution?
So if one string is a substring of the other.
Okay, good. That's, I have A, B, C. You can create a prefix, right? A, B. I cannot take BC because that should have been block 1 is B, blocks 2 is C, that I don't have. But I can truncate. Okay, that's an attack. So what do? I can just put the length also. In the first block, I also say there's a 3-block message, first block A, second block B, third block C. Okay, so that will now prevent you from just saying AB because it says, 3 block, right? Okay, what more? And these are all going to be part of the final solution for this. Right, so we need that, we need the length, we need the sequence number. What else? I had an example just now. I said, suppose I have ABC and AXY. Okay? Well, any two things which are length 3, let's say. Could you do something with it? So the adversary has MACs on two sequences, ABC and on something else. I don't know, PQR. Can you create something on ABR? There's nothing preventing you from taking the tag for A, tag for B, and tag for R, because it says block number 1A of a length 3 message, block number 2 is B, block number 3 is R that you pick from the other message. So you can splice messages together. Okay, so you don't want that. How do you fix that? Somehow messages need to have IDs, right, so that you cannot mix and match different messages. What could be an ID for a message? What's it again? Well, signature is not quite, not to mention that we have not talked about signatures, which is something different and relevant later. But maybe you're thinking hashes. Okay. You could do something like that, maybe, but I don't want to, this is not going to be our final solution, right? The simple solution. So I want something simple that does not involve hashes or cryptographic. Okay, you can just pick a random string, right, for each message. So that's essentially the whole thing. So I'm going to change each block so that every block has a random string that's going to stay same through the entire message. This is what will prevent the adversary from splicing things together. It will have the total number of blocks, which I'm calling T. It will have the sequence number, I, that this ith block, and then it'll have the ith block. Of course, I had to save, kind of make the block a little shorter to make space for all of this. But this is my new block, which I'm calling BI. And then you tag each BI separately. And that's actually a good MAC. Good in terms of being secure, but it's inefficient. It's very inefficient because its tag length increases with the message length. You have longer messages, you have longer tags. That was the solution for our, everything we have seen so far, right? The one-time MAC, this one, they all have very long tags, and we want to not do that if we can afford to. And here is one solution. Without the MAC is going to be just a single block, no matter how long the message is. Okay? Well, there's a catch, which I'll come to in a second, but here's what the CBC MAC is. So CBC stands for cipher block chaining. We saw this in the context of CBC mode for a block cipher for encryption. So it's looks almost the same. There is no initialization here. And more importantly, you're not outputting any of these tags in between, you're only outputting the last tag. Okay? An important catch or restriction is that, obviously it's not clear that this is going to be secure, but you can give proof that the secure with the following caveat: this length T is fixed. So this particular key will be used to sign only T block messages. Okay, you can pick any T of your choice, but I'll only sign T block long messages. What goes wrong if I allow this flexibility? Same key is used to sign different length messages. Well, then you should do this as an exercise. There's a length extension attack, meaning I can get MAC tag on some T block message, and then I can come up with a T plus first block and get a MAC tag, compute a MAC tag on the M1 up to them T plus 1 with one more call to the MAC oracle. So I'll get the MAC oracle to sign some other nonsensical message, but then with that and the original tag on the T long thing, I can create a MAC on a T plus 1 long message. Okay, so that's a length extension tag. So you need to fix that because messages are not. You don't want a different key for each message length. There are various ways to fix it, and there are many of them which are part of the standard. So these things like CMAC actually are serious MACs. So it's not just a toy example here, right? It's based on CBC MAC with a little extra something to prevent this length extension attack. There are two more things we will, if we get time, talk about once we see what hash functions are, something called HMAC, something called GMAC. They're also very popular, very standard MACs. Okay, HMAC uses a cryptographic hash function, GMAC uses a combinatorial hash function and a PRF. Let me see. Okay, I'll try to take a couple of extra minutes and try to finish this. So I talked about in the beginning authenticated encryption, right? You want to often do encryption and authentication. You can do it as encrypt then MAC. That works. But it's a little inefficient. You have to encrypt. Encryption is something like, say, you have n blocks, you run your block cipher n times, and say you're using CBC MAC, then you run your block cipher another n times to, even though you're producing only one tag at the end, you have to run your block cipher n times. So that's 2 passes of block ciphers. And that's a little inefficient. And, things like CBC MAC were probably designed to provide some sort of heuristic protection against tampering, right? So you could hope that maybe if done properly, you can get just one pass and get of block ciphers in some appropriate mode and get authenticated encryption. And it turns out to be the case. There are some modes which I won't talk about now, which are not in standards because they're patented. But then there are other modes which are, so the CCM is basically just encrypt then MAC, 2 passes. GCM, it's actually 1 pass of block ciphers and another pass of something much more efficient. So GCM stands for Galois counter mode. Something doesn't matter what it is right now, but it's just a particular way of running block cipher so that you get authentication kind of almost for free along with encryption. I sometimes mention NIST. NIST is a standards body in the US, and a lot of the cryptographic standards are, thanks to NIST. And the kind of relevant acronym here is AEAD, Authenticated Encryption with Associated Data, just allows more flexibility that some data need not be encrypted, only authenticated. Okay, so I'll take a few minutes to kind of sum up this kind of practical situation, right? Practical state. So stream ciphers, for us they were pseudo-random generators. What they really look like is just that, like there's one key and you get a stream out of it. A very popular but by now completely broken and outdated stream cipher is RC4, and the kind of more modern portfolio, a collection of stream ciphers are from this European Union effort called eStream. There are many more stream ciphers. You can look up Wikipedia and you'll get a list of stream ciphers. In practice, the stream ciphers also try to be a little like block ciphers. They also try to take an IV, which is not not a good idea in the sense that it has some heuristic goal to behave like a PRF, but stream ciphers were not designed to work like PRF, so it doesn't quite, you cannot use it like a block cipher. Okay, what does NIST say, or what are the most of the standards out there now do for stream ciphers is forget stream ciphers as a separate thing, just use block ciphers in counter mode. Okay, so just start, you have the key, and then that's like the only input that a stream cipher needs, and you can just start counting 1, 2, 3, and whatever the output comes out is your output of the stream cipher. So you don't need stream ciphers as a separate object often, even though it's a little simpler, maybe you can do it a little more efficiently, not worth the trouble. So often standard is to just use a block cipher in counter. Okay, so what about block ciphers? Again, there are several. From the, starting from the 70s or even before that. In 70s there was this DES and triple DES, so I'll have a slide about that. But the latest kind of standard is AES. Most common standard now is AES. These are all heuristic constructions, but very efficient, and they seem to do fine. Like nobody has figured out any attacks to distinguish them from random. And they have these additional features I mentioned. They're not just pseudo-random functions, they're pseudo-random permutations. Namely, it's a bijection from inputs to outputs. And the key, they're all built for speed, both software and hardware, and they withstand all known attacks. Attacks, we want them to be PRP, then you have to consider distinguishing attacks, but often what's considered in the literature are key recovery attacks. So setting the bar a little low, but still something. Okay, so this is the history of DES, the data encryption standard, standardized in 76. But even then, people thought the key length was too short, allowing the US government agencies to break this if necessary. And by the 90s, it was getting routinely broken. By 2006, it became really cheap to break it. And now you can do it in general purpose GPUs. It still will take a couple of days probably, but completely insecure, right, for an encryption algorithm. There are remedies, triple DES and DES-X, and so that this brute force attack. So this is actually a brute force attack that works, right? The key space is so small. So 56-bit keys, but there are various things you can do with it. So, but yeah, to fix this, to kind of expand the key space in some way, and those things are not broken, but not considered a good idea still. It was replaced by AES, and AES was standardized in 2001. And these things go through a competition, and many people try to break it. Whatever remains unbroken wins, and AES won that competition in 2001 and became standard. Now it's widely available on your processors. There are instruction sets for computing the AES. I'll skip this slide, you can look it up. Basically it's just saying, look, how do you know? It's all heuristic. There's no guarantee that these block ciphers will be secure going forward. What we know are various cryptanalytic techniques which have broken previous block ciphers, or take these block ciphers, weaken them, dilute them in some way, and then figure out how to break them. So as long as all those techniques fail against the real thing, it's considered okay. There are other issues like side channel attacks, which are not about the AES algorithm itself. It's about how they get implemented in software, for instance, right? So there are, so you'll see some of those in later in this workshop. Yeah, so the standards and standard protocols, like when you use HTTPS, they would be using AES today, and the recommended modes for AES would be to the CTR mode mainly, plus CMAC or HMAC as MACs on top of it. So that's encrypted MAC, 2 passes, but more and more people are using this AES GCM mode. It's essentially a single pass mode for authenticated encryption. Unfortunately, even though these are kind of very good things, there are a lot of old, broken things that are still in use because a lot of hardware and software out there still use them. For instance, apparently BitTorrent uses RC4, which is essentially a broken stream cipher. And also there's a lot of room for errors, not to mention the confusing terminology. People use hash to mean MAC, encryption to mean block cipher and whatnot. So hopefully at the end of this, whole workshop or winter school, you would have a better grip on these different terms. Okay, I think sorry, I'm not sure what that was. Okay, that's all I had for you. We have, I think I went over time by a few minutes, but if there is some quick question, I can take that and then you can break for tea. Any questions, or you're all ready for tea? Okay. All right, so the next session would be Professor Kameshri. I think she's outside.